Great. So my name is Peng. I'm from MIT, and this is a joint work with Ted Gibson and Roger Levy. And today I'm going to talk about rational inference from number agreement mismatch. So suppose you're encountering the following sentence: the gift for the kids are hidden under the bed. As a native or fluent English speaker, you might notice something surprising or unconventional about this sentence. You might recognize the grammatical number feature of the subject, the local noun, and the verb as singular, plural, and plural, or in short, SPP, which contains a mismatch between the subject feature and the number feature of the verb. But if I ask you the next question, what would you change? What would you do to change the sentence such that you can resolve this mismatch and recover the intended message of the speaker? Well, think about it for a few minutes, for a few seconds. Let's do a quick poll in the room just to see how people think about this. You might be thinking about multiple strategies or realize there are multiple possibilities at least on the table. So some of you might be thinking about adding the S to the subject gift, which is a subject correction changing SPP to PPP. Or you might thinking about that maybe the speaker intended to just talk about one big gift for multiple kids, and therefore you think they made mistakes at the producing the correct form of the verb, and therefore changing the verb from are to is. Well, raise your hands if you like the subject correction. There's no wrong. Okay, cool. Raise your hands if you like the verb correction. Okay, I think from the audience in the room, we see kind of half and half between these two options. And for those of you who didn't raise your hands, maybe you were thinking about changing the subject and local or changing the verb and local noun at the same time. Well, let's consider another example. The rug under the chair are made of wool. Well, clearly there is also a mismatch, and also we have this 4 different strategies on the table. And now let's do a quick poll again. How many of you like the subject correction? Raise your hands if you like subject correction. Okay, okay, barely. Okay, I see. Okay, how about the verb correction? Okay, I see very dominant preferences to verb correction in this case. So I think this contrast between the previous example kind of suggests that there are structure underlying our inferential behaviors in this seemingly mundane example of correcting subject-verb number agreement mismatch. But I think this phenomena kind of highlights a fundamental cognitive capacity of humans, which is that that humans achieve robust communication despite errors and noise in linguistic signals. In this project, we're interested in approaching this big question from this case study of resolving number agreement mismatch. And this is a particularly interesting case because, first of all, there have been empirical documentation of empirical phenomena that people engage with non-literal processing of subject-verb agreement in visually presented and audibly presented stimuli. And second, people in the linguistic literature have been studying the errors in producing subject-verb agreements a lot, and they review common and systematic patterns. And third, noisy channel theory of language processing gives us a way to specify the rational and optimal way of managing the processing uncertainty in linguistic input. So building upon these previous empirical literature and theoretical ideas, in this work, we advance and propose another theoretical ideas that if we think that the language comprehension behaviors can be understood as performing noisy channel inference in a generative model, and if humans want to maximize their utility of decoding other people's intended message, then a rational language user should develop a mental model of language use that is calibrated to the statistics of a linguistic environment. And under this theoretical framework, we have 2 specific predictions about this number agreement and mismatch phenomena. First, we predict that correction preferences should depend on the prior expectation over the possible error-free forms. And second, correction preferences should reflect an error likelihood function that is context-dependent and consistent with language production statistics. And I will illustrate these 2 points in the later part of the talk. So to test these 2 predictions, we want to formalize our hypothesis as computationally explicit models. And specifically, I'm presenting this full Bayesian model in the graphical model representations on the slides as a representation of what we think is the mental model in people's minds. And this model contains a three random variables: C, the communicative intent, and E, the error type during the production, and the O, the observed number mismatch. And for the comprehender, the job is to recover the kinds of errors given the observed number mismatch. So the generative story of this model is as follows. First, the communicative intent is sampled from a prior. In this case, we define it over the four possible combination of the number features of the subject and the local nouns. So that includes one gift, one kid, one gift, multiple kids, and so on and so forth. Now, given a particularly sampled communicative intent, the speaker might make an error. In this case, they might make a subject error or verb error, and these type of errors are dependent on the type of structure, on the structure of the intended message. And given a particular intended message, like the gift of the kids is hidden under the bed, and the type of error, let's say the verb error in this case, we can uniquely determine the type, the observed mismatch in this case. And the relationship between the observation and the C and the variable C and E are deterministic in this case. Now, the more interesting part is once we have this generative model, we can do inference. And what we are interested in is this posterior quantity of P of E given O, which is the inferred error type given the observed mismatch, which can be rewritten as proportional to the joint probability by implying Bayes rules. And notice that here we add this temperature parameter as an exponent of the prior components to serve as a strong test of the effects of the prior expectations. And we'll revisit this in the results section. Now we just walk through the full model. In contrast, we also consider alternative explanations, including the prior only and likelihood only model that solely attribute the variations in human behaviors to the variation in the prior or the variations in the likelihood. In addition, we consider another model that removes the link between the error types and communicative intent, which we refer as the context insensitive model, with no conditioning on C in the error likelihood function. Now, to compare across these four models, we want to collect some human behavioral data. So to do that, we designed two studies that takes the form of free-form editing tasks. They're basically just like what we do at the beginning of the talk. And we also conduct a norming task to collect people's prior judgments of the error-free forms. So for the free-form and optional free-form editing task, we basically designed 56 target items with the subject phrase taking this simple and consistent syntactic form of the noun preposition, the noun, with some examples on the slides, like the editor of the books or the contracts with the companies. And in addition to that, we also designed some filler items that contains one or multiple errors or requires one or multiple edits and contains different type of errors, so that subject will see a mixture of both the number agreement mismatch as well as other type of errors in the experiments. And we basically collect people's correction preferences. We record people's correction behaviors and compute the correction preferences across subjects. Now for the study one, basically the edit is required for each trial, and for study two, people can choose to skip a particular trial if they think there's no edit presented in the slides, in the trial. So for the norming task, we basically present a group of sentences like what we show on the slides to the subject and ask them to judge how likely someone might say it, rating a number between 1 and 100, and the average ratings across subjects normalized across subjects will be used as the prior estimate of the prior expectations. So far, to summarize these study one and study two, this editing task give us the error correction preferences, and the norming task give us the estimate of the prior expectation. And what we're interested in is the kind of relationship between them and how they could help us tease apart different models. So first, we want to compare across models by plotting the correction preferences derived from the fitted model on the x-axis and the one that we computed from the raw human data on the y-axis. So for the full model, we see that the model provides a very good fit, as indicated by the low mean squared error and high correlations. The prior only model and the likely only models provide a less good fits, as you can see, although they explained only part of the variance in the human behaviors. The context insensitive model provide a better fits than the prior only and likelihood only models, but still worse than the full model in terms of the mean squared errors. And we also perform a likelihood ratio test, and the statistics suggest that we reject the context insensitive model in favor of the full model, indicating that people's mental model of the errors are context dependent. Now, let's, at the very beginning, we talk about the two predictions. So let's dive into the specific effects of the prior and the likelihood a bit more. So first, we want to look at the prior effects. As we mentioned, we have this additional temperature parameters added to the prior in our models, and they are estimated from the data as well. The posterior of this parameter is significantly above 1, suggesting that people are very sensitive to the prior in their minds and maybe overrating the prior to a certain extent. And to show this effects maybe a little more clear in the data, I'm going to plot two quantities computed directly from the data. One is on the y-axis, I'm plotting the verb correction frequency, basically how likely people change the verb. And on the x-axis, I'm plotting the prior judgments of the observed subject phrase. So for example, the intuition is as follows. In this case, the gift of the kids are hidden in the bed. So suppose the observed subject phrase is more preferred a priori, then the subject is probably more likely to be correct, which will lead to a stronger inference that the mismatch is probably caused by a wrong number of the verb, and therefore we would expect higher frequency of the verb correction as the prior of the observed subject phrase increases. And this is exactly what we see in the human behavioral data. And looking at subset of data by the type of mismatch, we also see the similar high correlation across different trial conditions as well. Now, now we're looking at the second predictions, which is about the calibration between humans' mental model of errors and the statistic in the language production environment. So to do that, we will look at the particular parameters in the error likelihood function of the model. And we will first try to compute the statistic in language production using data collected from other people's studies, include the Riskin et al. 2021 and Kendo et al. 2022. So the Riskin et al. Studies, they are all language production studies, and the Riskin et al. Basically ask people to produce using visually presented sentence prefix completion paradigm, like the key to the cabinets, and the prefix flashed for a few seconds, and the subject are asked to retype the prefixes and continue from there. And the Kendo et al. Using a scene description paradigm, with the novel objects on the screen, and ask subjects to produce a description of the scenes, like the pinky above the greenies is miming. And their data record the specific production of the sentences, and we can find out the error trials in those data sets, and then calculate what is the frequency of different type of errors given the specific intended messages, grounded either on the prefix or on the visual scene. And this is what we see in the human data. Now, on the upper row of the slides, I'm plotting the model parameters that we estimated based on the editing task that we perform in this study. Probably across board, we see a visually qualitatively similar patterns between the statistic computed from the production task and the one we estimated from the editing or the comprehension task. Overall, we see higher verb errors in human productions, and this is also what we see in the models as well. But maybe more interestingly, when there are certain cases where humans tend to make more subject errors, and this is also what we see in the model estimated model parameters from the editing error correction task. So I think this provides some evidence in support of the idea that humans' mental model of error likelihood are calibrated to a certain extent to the linguistic environment. So to conclude, in this project, we present a case study of how humans infer errors in language use to achieve robust communication. We develop a probabilistic generative models to understand the inferential structure underlying error correction behaviors. And the modeling results suggest that humans closely track prior statistic over linguistic forms and deploy a context-sensitive model of errors in noisy channel inference from number agreement mismatch. I want to thank Rachel Risky and Matt Kendall for sharing their language protection datasets, and thank you for attention.